This is February March 065, paper 62 as an ATB paper. The first question is about measuring measurements with beam balance. So let's see what he has to say about the question. So this is a common question in terms of finding the distances. So he's asking you to find out the distance d of the center of the load from the zero end. So we want to find the distance from this point up to this point of the load or of the coin. So we can see that there is one mark over here that's visible, and there's one mark over here that's visible. So this will be approximately 26.5, and this will be 29.5 because it is behind 30. So since we want to find the distance, and it generally goes up to the center of the point, so first we can find this distance and then simply divide this by 2, and then find it from 0 up to this point. So this should be 29.5 minus 26.5 divided by 2. This comes out as 1.5 centimeters. Now this is 1.5 from this point onwards till the center. So this is 1.5 centimeters. From the 0 mark, we can visibly see up to 26.5. The next 1.5 are actually hidden beneath the load, and we can't see that properly. So we're simply going to add 26.5 to eventually get to 28 centimeters, which is the true reading of this distance. Part B says the student adjusts the position of the meter rule until the pivot. This is again a common question. It says describe a technique to ensure the rule is as nearly balanced as possible. So you keep checking on the ruler by moving this load either back and forth as it tries to tip either on one side or either from this side. And the absolute certainty we have is when this is balanced, or this ruler is balanced, when we are sure that the slightest change either tips it completely to this side so that the ruler actually touches the ground over here, or it generally touches the ground over here with the slightest disturbance. That is when we know that it is absolutely perfectly balanced, and any matter or any point of external disturbance will change its position or will start to cause its movement. So we say that the ruler is considered balanced when it tips both ways with the slightest displacement or the slightest change. The next question is, the student finds the ruler as near as possible and it's being balanced in the pivot. And he says that when the pivot is at 47.6 centimeter mark, this is important, it will be coming in handy later. Calculate the distance A by using this formula. So you found D in the previous part, which was 28. So you might be tempted to try to figure out these dimensions on your own, but you really don't have to, because the instructions will always be clear in every exam that you can expect. So this should be simply 50 minus 28, which will become 22. The next question is position of pivot minus D for the value of B, and the position of pivot from the distance is, or from the end, is 47.6. So this point, you can say, is actually at 47.6, and then this one goes to 50. So since this is supposed to be done for B, so this will be 47.6 minus 28, which was our D in the previous part as well. So this will come out as 19.6 centimeters. So this will be 19.6. The next part is part C, and we have to draw a graph in this situation. We have different variations for that, but let's try to figure out the scale for the graph. He says that moves the load that its center is above the 5 centimeter mark, then you repeat the experiment with these new positions. That is completely fine. Now he says that we're going to draw A on y-axis and B on x-axis. So the first thing that I would do as a student is simply write down using a lead pencil that B is x-axis and A is y-axis. This helps me to quickly figure out, or quickly just locate the coordinates when I'm plotting the points on the graph. So the first thing to get these full 4 marks would be to just label the sides with A/ with the unit and B/ with the unit of that side as well. This is the first thing that you should need to do, and just get it out of the way so that you can simply resume working with the question. Now he does mention that you don't need to start the axis from the origin, which means it can be from any other origin or any other point as well. So if I go to x, first let's figure out x. The minimum value is 22.5 and the maximum is 40. What I could have done is, if I look at the x-axis, I have this starting points and these are the coordinates that I have. Again, I'm going to explain to how to make a choice. You could disagree with this and you could just go with the simpler version, which is absolutely fine. But we will discuss the problem with the simpler version. So let's say you start with 0, 10, 20, 30, 40, and 50. This is absolutely correct in terms of the scale mark, but this has a problem in terms of the spread of values. You see, the graph starts at x and finishes at 40. So technically, on the x-axis, you will have the smallest coordinate you will have would be around 20, and the largest one would be at 40. So the only region along the x-axis you will be covering will be this much, which is less than 50% of the total graph. So your points will come out as really close to each other like this if you did that. So what I would advise you is to choose a scale which is a bit more spread out, because it's telling us that it's not a permanent condition. We can choose any other scale as well. So I would start with something like 20. I will have 30 here and I will have 40 here. So this will become 25, this will become 35, and this will become 45. Now, I can expect that the graph is going to start at 22.5 and finish at 40.5. So I can expect it to start somewhere here and finish at probably somewhere around here. So from this point to this point, I will see a nice progression of coordinates spread out more and covering more part of the graph as opposed to what I had selected previously. Counting boxes and coordinates is your task, is your job. I will share a technique for that, but you have to be really good at that. So for y-axis, it's a bit tricky. You see, we have one less box. We have less space as compared to x-axis, but we still have to fit 25 to 45. So if I start with, let's say, 25, and this is 30, and this is 35, and this is 40, then this becomes 45. Now, I do incorporate 25 on one extreme, and I'm successfully incorporating 45. But if I start with 20, however, for example, if I start with 20 and make this 25, and this is 30, 35, 40, then there is a problem. The problem is that I won't be able to see 45 again. So the largest value will not be fitting in these circumstances if I do it this way. So by chance, I have to make sure that this starts with, let's say, 25 minimum. But again, this begs the question that the graph is going to start from a very, very close edge of 25. So to get around this problem, we would have to settle down for a smaller scale. So it can be starting from 0, 10, 20, 30, and 40. Now, in this case, if you do that, you would still have a nice progression along the y-axis, because the values are 20, 25 to 45. So we will be having 20, approximately, yeah, 25, 30. So we have something around this area. Then we have 35, sorry, 30, 35, 40, 45. So eventually we have 30, 35, 40, 45. So we will be covering an area expected along the x-axis. The area we're going to cover is going to start from approximately 22.5, which is somewhere along this line, and end at this line along the x-axis. And along the y-axis, we are starting from this point and ending at this point. So our coordinates would lie along this line, right? Which is, again, really, really border edge of what examiner says is supposed to be with more than 50% of the graph. So again, I would go back and adjust the y-axis so that I can cover more than 50%. So indefinitely, of course, I have to settle down for something much more on the edge. So if I start from 25 and choose 30, 35, 40, and 45, then my graphs actually start from this point, let's say, and this point, and they end at this point with 45 being the last coordinate. So I would be covering this much amount of area for this graph, at least for the coordinates, which will be a good choice. So again, count the number of boxes, be careful that you're making this choice. What I would advise you to do is that if there is a space of 5 boxes, then this will be 5 divided by 10, which would become 1 by 2, which is 0.5 per box, per tiny box, right? And along this side, this would be again 5 divided by 10, which is 0.5 per box. So make sure that you're counting the boxes correctly. Once you've plotted the coordinates, I'm just doing it randomly, just draw the line of best fit. Once you're done with the line of best fit, be advised, every single time you have to do this, please be advised that the gradient will be taken by coordinates on the line. So for example, if this is your line, you've done, let's say these are your coordinates from the graph, with the graph of best fit or the line of best fit. Please don't choose these coordinates for the gradient. This is incorrect approach. Choose coordinates from the line and make sure that the line that you choose is again more than 50% of the total line. So what I generally do is choose a coordinate from this section and choose a coordinate from the last section to ensure that there is not going to be a single chance that my line is going to be less than 50%. Although you can do that, but it won't be marked, it won't be given credit for. So I will choose a coordinate from this location and a coordinate from this location. And of course, I will mark them as a circle, or I will put a circle on them to tell the examiner that these are the coordinates I'm using for a gradient. But on a side note, if you just add a triangle with a dotted line, with a ruler and pencil, of course, to tell the examiner that this is the triangle that you're using for gradient, I'm just going to add the coordinates that I've taken from my graph. So this is 10, 12, and 37, 41. Mentioning coordinates is important. And then you just simply write down the formula for gradient, that g is equal to delta y divided by delta x. It's a good idea. Then write down the values replaced. So this will be 41 minus 12. This will be 37 minus 10. And then, of course, g calculated will be 1.07. But since we are going to two significant figures, this will be 1.1. And in this question, it will always be a range given to you because he understands that students will have variation in their answers. The next part is using the value of gradient to find the value of m, where k is already given. Again, a good idea is to replace all the values. So this will be 25 divided by 1.1 minus 1. This comes out as 357, which after two significant figures is 360. No units are given, so we will not be adding any units to this. The accuracy of the results obtained by the procedure depends on the meter rule. Okay. Without a load balancing the pivot at 50 centimeter mark, student finds that this does not happen. She adds a small piece of modeling clay at one end of the ruler to correct it. Suggests if this suitable change is good enough for the experiment. You see, in this particular instant, both answers were correct, but it should have been backed by the correct explanation. So if a student says, no, this is not the right practice, that person should have said that it disturbs or mass of clay changes mass of the ruler or the full system that we're trying to measure the center of. And if a student says that, yes, this is fine, this is absolutely correct, this is absolutely right, there's no problem with this, then they should have justified that the mass of the clay or the piece of clay is insignificant, or in terms of percentage significance, or in terms of its importance compared to the mass of the ruler, is too low. So adding this would not disturb the result of the system or this experiment. Question number 2 states that we have a circuit that we're going to use to verify a few rules. There are 3 circuits which are going to be probably identical, but he hasn't mentioned that here. There is a circuit A. They're connected in series. He says on the figure, draw a voltmeter connected to measure the potential difference across P and Q. So please use a ruler and add a voltmeter like this. You could have done this from this side as well, which is also right. So no problem with that. But I'm going to likely leave only one of the choices so that anyone coming to this video would not be confused by that. We're not drawing 2 voltmeters. We're just drawing one, but with 2 different options. Part B says that the current, the student measures the voltage, the student measures the voltage and ammeter. Voltmeter is connected. This is ammeter, this is voltmeter. We want to read these values and put them into the table. Now be careful about these values. This is going to be 3.1 and the current is going to be 0.12, I suppose, yeah. So if you notice that this is from this point to this point with 10 divisions, which clearly makes this 0.1 per division. So we can very clearly or very easily achieve this value, which is going to be 3.1. But this value for current might be a bit tricky for us, might be a bit tricky. So you see, if from this point to this point, it is 0.2 in 10 divisions. So that would be 0.2 divided by 10, that becomes 0.02. So every single small division would be 0.02. So up to this point, I can believe this will be 0.1. And the next step, which is shown by the needle, should be 0.12. So again, your choice. You can find another method. You might have normalized it by your own method. It's completely fine. So we have added these values on the table. Then he says there is circuit B. And then he says that there are going to be certain values on the table. Circuit C with certain values. He says use the formula R equals to V over I and fill in the rest of the values. So let's calculate those values and we will get 25.8 ohms. We have 13.2 ohms and then we have 3.02 ohms. Now, he does mention at a certain part that we need to add the column headings of all these values taken. So this will be simply volts, this will be current as amperes, and this will be ohms as resistance. Again, everything is still, up to this point, is still a repetition of the previous past papers that has already been asked from these topics. Okay, now he says we want to verify whether RA, RB, and RC follow these rules that he has devised or is trying to test. So from the table, we had the value of RA to be 25.8, which is being divided by 3. Now, if we go back, this is 25.8, and this will be RB, this will be RC. So a good idea would be to just quickly write down those values over here so you don't have to go back again and again. A practice to save time. This will be 13.2 divided by 1.5. This will be 3.02 multiplied by 3. And the final answers come out as 8.6, 8.8, and 9. I think it's 9.16. Yeah. So 9.1. Let's save it at that. 9.0 something, but it will be 9.1. Yeah. So student investigates or suggests that RA, RB, and RC should all be equal or they are identical. This is what I was expecting at the start of the question, if you can remember. This is where I paused for a moment, that it should be something like this, but let's see if it is. So he says, what do you think? Are they equal? And if they are, then try to justify your statement. Why are you saying it this way? So for me, according to me, I will say that they are identical. They are definitely, they're identical, or they are exactly the same, or I agree with this statement. Simply, I agree that RA is equal to RB equals to RC. No problem with that, but what would be the justification? Again, a repeated common question. We would justify by saying that they are within 10% experimental accuracy or limit of experimental accuracy of each other. Yeah, so that is how would you justify this. And if you want to test your theory, what you can do is choose any one of them, either 8.8, 9.1, or 8.6. Give it a 10% plus minus addition into the same value. It will give you a range of values from RA minimum to R max. And all of these values, or both of these values, will fall into the same category. And if they do, it means that RA, RB, and RC are practically exactly the same, or they are going to be considered the same, even if they have minute differences in their values. A student investigates the resistance in circuit A using a variable resistor. He says, draw the symbol for variable resistor. Very simple. We have the symbol for variable resistor is going to be this one. If it had been for a potential divider, then we would have to draw the symbol of a rheostat. That's for another question. This is the answer for this question. So just one advantage using a variable resistor to change the current in the coil. So what would be our advantage? You see, whenever we are carrying out experiments to gather data, or at least trying to repeat the experiments, it's always good to have a certain element that we can change more than once, or at least try to change more than twice or thrice. So we generally find that changing or having at least 5 set of values is a good experiment. But when you go to A levels, this will generally be pumped up to at least 6 values. 5 is bare minimum, but 6 is a good, 6 coordinates are good for a graph. And anything more than that is always a plus. So state 1 advantage. So we can get range of values. We can get range of values because for graphs, we need at least 5 points. You can add the rest of the statement. I'm just adding prompts here, what you're supposed to write down. Question number 3 is again a complete repetition of past paper questions. This is common in O levels and IGCSE physics. So he says the student set up the experiment 3.1, suggest one precaution that must be taken. These are again common precautions. Object lens must be at the same height and lens perpendicular to the bench, which means it cannot be like this. It cannot be sat like this. The lens couldn't be at an angle. It should be completely perpendicular. We need to make sure that it's actually making an angle of 90 degrees with the bench so that all the light rays coming towards it can be focused properly. And we're absolutely sure about that. Fix the meter rule to the bench. Now, this is a good practice. Now, what we do generally is add a meter rule on the side. Of course, it's being drawn in 2 dimension. And we clamp this with the rest of the apparatus and trying to measure all the distances like U and V or focal point by the ruler. And we do make sure that these distances are considered from center to center, or at least the point where they're going to be formed. And the reference point stays the same for the rest of the experiment as well in terms of fairness. The next question is student sets the distance U between the luminous object to be 20 centimeters, which means that U is probably 20. He places a screen near the lens and moves the screen until a sharp image of the illuminated object seen on the screen. Okay, fine, that's good. Describe a technique for obtaining an image that is sharp as possible. Again, move it back and forth gradually until a sharp image is seen. A repeated question. It says measure B1 from the diagram 3.1, and since it was 1/10 the scale, it means it was being shrinked to be drawn on this piece of paper 10 times. It means in reality it will be 10 times much larger. An example of this would be the objects around you. You see, if you're looking at a laptop screen right now, or if you're looking at a phone screen, you can still see it. Its image has fit inside your eyes, or it can fit inside your eyes. So it was being diminished for that matter. So the same thing is happening here, that in reality, this could be 10 times bigger, but it's my choice. I can draw it much smaller. For example, if I draw this vehicle, again, this is much smaller from the real car, and we can do that. It's fine. So we measure the distance V1, which should be, again, from this central point to this point. Don't measure it from this point or this point. It should be center of the lens up to the plain white screen, and this will become 8 centimeters. Generally, it is by 1/10, so we'll have to multiply this by 10 to find the full scale distance, what it actually is going to look like if it was being measured from reality. Okay, so the next part, we have a bunch of measurements from these diagrams. He says measure H0, we measure H0 and HI, and then he asks us to find the magnification. Now in P2 and P4, the formula might not be given to you. So please be advised, always write down how you got these values. Where did you pick up HI from or H0 from, and then find out the answers for the examiner. So this is going to be 4.0, which is written already here. It says calculate D. Again, we simply have to put in values, but be careful. Please do show the values. So magnification is 4 plus 1, which is going to come out as 16. So this will be focal point, or the focal length will be 16 centimeters, I believe. Yeah. So describe one difficulty, and this is again a repeated difficulty for these experiments, how to form an image. Now the problem is in this experiment is that you will see the image on the screen, but it will be a bit blurred, or because there's a lot of distance between the lens and the image, it will be a bit blurred, and measuring its height is not really that easy. So we first identify the problem, and that is the difficulty. That sometimes the ruler gets in the way, because if you're a person and you're looking at a piece of paper, and there is an image in front of it, and you want to get the distance of the object or height of the object, then definitely holding the piece of paper and the ruler at the same time will be a problem. So the best idea would be to use a translucent screen, which is a bit, you can say it's transparent, so some light can pass through. So we can stand on the back side and use either a clamp or a ruler or just plain blue tack to stick it with it. The best idea would be to use a graph paper instead of a plain paper. You see, if you're using a graph paper, you would definitely know how many boxes the image has taken from you. So how many boxes are going to be covered. So this would be the best answer in these circumstances, which I've mentioned here. Now, the next part is for the student to adjust the position, there needs to be a V2 for this much. Then he says calculate F2 by using this formula. So we had U as 40. This is 25.1 as given in the question, replaced directly, divided by 40 plus 25.1. This is our F2. This is the second method of measuring the focal point. This comes out as 15.4. Now he says, are they together? And suggest which value focal point might be more accurate. Explain your answer. So F2 seems to be better as F1 has smaller measurements and lead to a large percentage error. What does this statement mean? You see, in F2 or in this focus point method 2, we can very clearly see that in this case, we had very large changes in diagram. So these lines are generally blurred out because it was being magnified. So if the lines are blur, you won't be able to see that should I be counting the box upper side or should I be counting the box's lower side. Same problem over here. But when you do it this way, when you do it with smaller values or smaller measurements, the percentage contribution of every value also decreases. Now, since the contribution decreases, the error in the measurement also decreases. So that's why we have an advantage of F2 over F1 method. Let's move to question number 4. Again, a repeated question about cooling curves with insulation with a bit of a twist. He has given you these equipment already. He has given you some source of hot water. Now, I would advise you that if you just follow these pointers straight away, without even having a sequence of thought, you will still get, if this question is, I think, is for 7 marks, without even thinking, if you fill in or answer these 5 questions, you will get 5 marks out of 7. But let's see how to get those extra 2 marks out of these 7-mark questions. What can I say that are much more than these 5 questions that he's asked us? 1, 2, 3, 4, 5. So let's move on. It says list any additional apparatus that we might need. So what we might need in this one is a thermometer and a stopwatch. Always a common answer for cooling curve graph. So I've done this one. I will advise you to put a small cross or a tick on these points so you can remember what you've done already. Explain how do you do the experiment? What's the procedure of this experiment? What are you actually going for? Which one is an independent variable? What's a dependent variable? And what would you be likely keeping constant? All of these things come into point number 2 and 3. So we are keeping the volume of the water added and the initial temperature as constants. One of the constant mentioned would have been good enough. But if you mention 2, you get an extra credit. As I said, this is a 7-mark question. So if you add extra information, they do give you credit for that, apart from those 5 points that you still have to answer. We measure the initial and final temperature using thermometers. Always tell the instrument that you're using and why you're using that. We're going to vary the layers of insulation, maybe 1 layer, 2 layer, 3 layer, and so on. This is our independent variable. This is what we are changing. And as a result of that, we're going to observe what's the final temperature of the system going to be after a set amount of time. So I'm not changing the time, I'm changing the number of layers. And I'm fixing the time for my measurements. Of course, it can't be done for every 30 seconds. You could have done that, but it will only be for then 1 layer. Then you'll have to make another table for 2 layers and 3 layers and so on. So since it was going to be a bit more hectic, I have fixed the time for this. Or what we can do is we can fix the final temperature that the final temperature has to be room temperature, and we're measuring the time to reach that final temperature or the room temperature. That could also be one of the options to do that. So then we have we draw a table, and be careful the table that, because the experiment that I'm choosing deals with number of layers and initial and final temperatures, and I have fixed that the time taken between final and initial temperatures should be 5 minutes. I should wait 5 minutes and see what's the change in temperature. Now I will not be adding time into this table. It doesn't have to be, because I've kept this as a constant. Now the next part is to make the table. So I've added the table, but there's one thing that's missing, and that is the units. So this should be degree centigrade. This should also be degree centigrade. This should also be degree centigrade. And since number of layers doesn't have a unit, or you could have done, let's say, thickness. If you had added thickness, then it should be unit of centimeters. Okay. All right. So the next thing is explain how to use the readings to reach a conclusion. Now, you see, you have taken the reading. You've populated the results. You have filled everything in this table. What do you do with them? So a discussion around the cooling rate would be good. A discussion around the fact that after so much time, the number of layers which had, or the jar or the experiment in which we had the highest number of layers was had the highest final temperature, or had the least change in temperature, because it was so insulated from the environment. Now, don't add any theoretical explanation. Just add a conclusion based on what you already know. You don't need to back it up by theory. The theory says this: there is no conduction, there is no convection, there is no radiation. He's not looking for that. He's looking for a conclusion that if you had seen this graph like this or like this, what could you have said about these cooling curves? Which one is a better insulator and which one is not? An added benefit again for this would be to add more information, and extra information is how many readings would you take. This is also an extra credit. Also, you will see that some students write down, repeat the readings and take average. Now, this is the examiner's report. I would advise you to read the last statement. You can pause the video to read the whole statement, but I want you to read the last one. However, repeat the experiment was not accepted as a suitable response here. As I've mentioned in my classes and my lectures many times over, that repeat the experiment is not the right answer. It's a vague statement. So instead, what you can do is tell him to repeat the experiment, but after repetition, what should he do? What should the person do? So repeat the readings of temperature for the same number of layers and then take average. What does that mean? It means that if you take initial reading and final reading, okay, change in temperature comes out once. This was with, let's say, 1 layer of thickness or 1 centimeter of thickness. Do the same experiment again with 1 layer of thickness. There will be of initial temperature, final temperature, and a change in temperature. Now you have 2 change in temperatures, delta T1 and delta T2. For 1 layer, you have 2 readings. Now take their average to find out the average change in temperature for 1 layer or for 1 set of readings. This is what we mean by repeat and average, or repeat the experiment and then take average of the readings. So you need to make full articulate sense of that. Just writing down repeat and average would not get you any credit. So this was also a good practice in terms of exams attempt. So apart from those 5 questions that we've addressed, apart from these 5, we've added 3 extra points in this account, and the total marks were 7. We've added 3. So 5 plus 3 puts you at 8 points, or you'll get 8 marks for this, or you should get 8 marks for this. So it's still a lot of room. You just have to get 7 out of 7, and you have 8 chances to get there, and 5 are exactly right in front of you. So you just have to make 2 more comments about these experimental setups or procedural questions. One of them will always be repeat the experiment and take the average of the final value. One of them generally would be to draw a graph between X and Y. One of them would generally be a safety precaution for this experiment, which could be added that since you're dealing with hot water, use gloves and goggles so that your hands and feet might not get burned if it accidentally gets spilled. Although it was not asked from the examiner, again, it is good practice when you're dealing with high temperature objects high temperature liquids to suggest a safety precaution. That is general technique for these questions. That is all for today. I hope this paper has helped you. I hope to see you again.